In the vector data model, each of the things that we would call, we haven't introduced them yet, but each data set, and we can have a point data set, a line data set, a polygon data set. Um, each of those has associated with it in the software that we use, ArcGIS, and other forms of software that do GIS analysis. They'll have tables that directly link to those point, line, and polygon features on the Earth's surface. And we can attach or insert in those tables just about any characteristic that makes sense that is applicable to that feature. So, for example, what we're seeing here on the map is three states that are highlighted in blue: Washington, Idaho, and Montana. And then every row in the table that relates to one of those states is also highlighted. We can also see that in the table there's a lot of information. Um, the FID column tells us the feature ID, which feature we're actually looking at, has an individual number. Each state, therefore, has an individual number. The shape tells us if it's point line or polygon. And then we start getting into the characteristics. Well, what is the polygon? The state name, Hawaii, the abbreviation, Hawaii, population of Hawaii in 1990, population of Hawaii in 2000, population 1990 in square miles, number of households. So every header of every column gives us an idea about what information is in there. And if we needed more than that, there's a place in each data set that we can examine called metadata that'll give us more information about those data columns. Okay. So anyway, this is the basic that we have, the basic way that we store information about points, lines, and polygons. There's a lot of other characteristics that can be in there. It can measure area. It can measure length of lines, areas of polygons, things like that, and any other characteristic that we can put in there. And it doesn't necessarily have to be population characteristics. We could put in environmental characteristics, but it doesn't make a lot of sense to do a whole lot of environmental characteristics at the state level. We usually would use smaller sized polygons, or something else they're called is enumeration units. Um, so if we broke the states down into counties, we might that might make a little bit more sense describing some physical features, but we could always talk about the counties and their individual characteristics within each state, or we could break them up into smaller pieces like the U.S. Census does, um, with its um, levels of studying population in the U.S. using what are known as blocks or block groups, census tracts, which are just polygons at different scales describing area and then counting characteristics about the population within that area. Okay. So whatever scale it is that we have in our data set, in this case it's state level within the United States, we can analyze that information and it'll tell us something about, in this case, population characteristics within each state. In ArcGIS, where data gets stored on your hard drive, there are a couple different ways that we can do that, and we're going to learn them, and you'll get exposed to them in the exercises and the practicals that we have in the class. Um, Feature classes are going to be your points, lines, and polygons, as you're seeing here in these examples. Um, the feature class is a specific name that we use for vector data, which is stored in something called a geodatabase. So ArcGIS has several of its own data, proprietary data types. and containers. And a geodatabase is a container for feature classes. Geodatabases can also contain raster information. But whenever you see the term feature class, that specifically means a point, line, or polygon feature, or combination of them, that's stored in a geodatabase. And there are some advantages to using geodatabases we'll see later in the semester. Um, but in any event, just know that the feature class is vector, stored in a geodatabase, and you need to inspect each one to see whether or not, see what it is. If it is point, line, or polygon, and to see what attributes are actually stored in the table. And the attributes, again, are the columns of information within each table. And they're going to be different depending upon why the data set was created, what the data set is intended to describe, and which attributes related to either the physical surface of the planet or population characteristics that were intended to go in the first place. And so feature classes will be either one of those three things: points, lines, or polygons. So there's two different ways that we can describe vector data, and I'm just pointing them out here because you may run into them in the scientific literature and sometimes in instructions for how to run a particular data analysis model or something like that. Georelational and object-oriented. So in a georelational vector data model, features, as it says here, the features and attributes are stored separately, and they're linked together by a common feature ID, which means there's two different tables. One of them is for the geometry of the vector data set, and one of them will be for the attribute data, and they're linked by a feature ID, which means that each feature in the data set has a unique number or ID, and all the attributes in the tables are going to match that. They're going to be linked to that ID. And this is for older data sets that we still encounter and use regularly in ArcGIS. They're georelational. Object-oriented data models store features and attributes together all at once, and that makes it a faster running form of data. You're able to do the computations quicker. That really doesn't really matter all that much these days, and if you have one or the other using a modern computer, you're really not going to notice the difference in computation time anymore. That has really pretty much gone away. But the older data sets in vector model, shapefiles and coverages, which we'll come to later, those are the older styles of storing data. And some agencies and corporations will still store things in that because they're just used to it. And they function pretty much just the same as your object-oriented model, which would be feature classes stored in a geodatabase, is an example of that. They're all going to run about the same in terms of how quick your calculations will go. And when they were first introducing the object-oriented model, that was an advantage of the object-oriented model, was that it would be able to compute things faster. But since computers are now running very fast and we have lots of memory and storage space, the differences between these things are really not so drastic anymore. And you will encounter both georelational and object-oriented data, and it's not going to slow you down one way or the other. You're just going to be able to use it in ArcGIS pretty much interchangeably. So, advantages of the vector data model is that it's inherently designed for storing discrete objects. So back at the beginning of the lecture, we talked about discrete versus continuous information. Vector is better at discrete objects, at describing points, lines, and areas, and very precisely locating those features on the Earth's surface. With the tables that we can associate with those geometric features, you can store thousands of different attributes easily in a table. And when you start looking at geodatabases, millions of characteristics and attributes about things. And so they're very powerful in terms of storing and managing massive amounts of information about the features they describe. Um, Pretty handy in cartographic applications, which we'll see. We can change all sorts of different characteristics about how they look on a map, color, shape, texture, all those different visual characteristics. Relatively compact compared to raster data. They're going to consume less disk space overall, although some of them can get kind of large. Rasters will get even larger, exponentially larger in size, trying to describe the same information. Um, and that becomes, again, kind of a lesser of a problem these days with the massive amounts of storage that we have available to us with terabyte hard drives, and the advent of larger and larger capacity hard drives every year, and other storage systems. So, um, anyway, the last point here, vector data is ideally suited for analysis of areas, lengths, and connectivity between places. So, because it is much more accurate in its description of locations and shapes and areas and the lengths of things compared to what we have available in the raster data format. And the raster is much less well suited for analyzing things in specific aerial comparisons or the lengths of linear features on the Earth's surface. It's not even close. The vector data is so much better for that. And so what will happen in most projects is you'll wind up using both data models for different things. We're going to be focusing on vector data for the pretty much the first half of the course, and exploring what we can do with them in a lot of different ways. And then we switch over to emphasizing raster data the second half of the course, and combining both of them in how we analyze and describe and depict natural phenomena and cultural demographic phenomena of the Earth's surface. So raster is essentially a series or a grid, you can think of it, an array of squares across space. And they, like vector data, have an XY origin point. And if you know where the origin is, and how the program kind of works is it has an origin point, and you feed into the data set what the cell size is, meaning the length of each side of a square. And then the system knows how to draw the raster just from that information right there. How many cells to the north, how many cells to the east, and it'll just draw them out. And then in what's stored on your hard drive, each cell has a unique identifier, and it has a value. Usually just one value in most raster data formats. Some raster data formats will contain more than one piece of information. We'll explore that in more detail later. But essentially, what you're looking at is rows, as the picture's demonstrating here, rows and columns of pixels. And sometimes a GIS system will figure out where you are by counting, well, you're in the 15th column of the 45th row out in the raster array. Most of the time, we'll probably be dealing with latitude and longitude coordinates, things like that, because these rasters are most often georeferenced to the Earth's surface, meaning that the XY location, the origin point, is a known point in space on the Earth's surface, which, if I didn't mention it, also occurs for vector data model. Those are also georeferenced. But here it's a little bit something really need to point out, because these squares, they're really generalizing things about the Earth's surface. So what we're saying here, let's pretend that this is a 30-meter grid. So every side of a square is 30 meters. That means that we're generalizing all the characteristics on a 30 by 30 meter square into that one unit. And so, you're taking the footprint, maybe of a house, um, a large house, and saying this one value in this raster represents that value. Um, or think of this in terms of elevation, where the colors are representing different elevation values, from the light green, lower elevation, to the white, higher elevation ridge lines and peaks. Okay, each of those 30 by 30 meter grids would have a value of elevation in it, and basically we're pretending that the elevation is flat and square within that. Um, and so we're losing some of the ability of our vector data to describe individual points on the Earth's surface. So we're using a larger area to describe um, the Earth's surface, and so we lose some of the details in that. Okay, that's something to think about between raster and vector data. Vector is much more accurate. Raster generalizes a lot more, but it allows us to do certain kinds of analyses that we cannot do in vector data model as well. So there are two different ways of storing information about the Earth's surface, and there's benefits and drawbacks to both of them. We can do pretty much the same information in either one. However, we've always got this limitation in raster data that it's always describing areas on the Earth's surface as squares, whatever cell size the squares are. That's something that you can't get away from. That's always going to be a limitation of how accurate the raster data can be. You think about trying to describe a road with 30-meter grid cells, and there you're going to run into a problem. Okay, or you're describing any other type of linear feature, a river across the landscape, as a 30-meter cell, because every cell in the raster has to be the same size. So what happens if the river takes up less space than 30 meters, but you want to make sure that the river is shown in the raster? Then it has to be that whole raster cell. So you start getting an idea about, well, yeah, that's kind of a major limitation of what this can do. And so there's some forms of information that we generally will not show as raster because of that, and rivers and roads are some of them. We would much rather show those and analyze them as vector information because they're discrete objects. For surfaces, raster is much better. It shows the entire surface. It has no breaks in it. And so there's certain things that we can just do better with it. So anyway, there we go. Okay, so I referenced this on the last slide, a digital elevation model, or a DEM, which is what I'll more commonly use for the throughout the class to refer to these things. Whenever you see that word DEM, it's an acronym for digital elevation model, and every cell in the raster contains a single elevation value, and they're spaced out on that grid, whatever the cell resolution is, to describe the surface. So DEMs are actually pretty useful, and you can derive a lot of other types of surfaces from them, which will actually be the topic of an entire chapter later in the class, or a unit later in the class. But essentially, if you think about what a raster is, this is a really good example. It typically contains one piece of information in the cell, other than the spatial location. If you were to go into the GIS and hover your mouse over any one of these cells, it'll give you a reading in latitude and longitude, or a universal transverse Mercator location, grid coordinates, whatever coordinate system you're using. But each cell typically only has one piece of information in it, and in this case is elevation. So here's what a DEM looks like. Other rasters would work pretty much like this too, where Even if we derived something from this, like we can derive slope, we can derive compass direction, which way each cell is facing, north, south, east, or west. Each of those derived rasters or derived surfaces is only going to contain that one piece of information in the cell. So if we're using the raster data model to analyze the Earth's surface and characteristics of it, we're going to wind up needing more of these, more data sets to describe what's going on the Earth's surface. The vector data model can store many multiple attributes in a single table. So if we have a single vector data set that's doing a pretty good job of describing things on the Earth's surface, we can contain all the information that we want, basically, in a single table. But raster data, we wind up usually needing one raster data set per characteristic. And so it adds up really quickly, and the raster data takes up more disk space in general than vector data. So there's another kind of a trade-off of using raster information rather than vector information as a primary data source in your analysis.